species diversity, and we don't want to do that because that doesn't make any sense to us. So one of the things the ecologists did that the chemists should have done with the pH scale is made it so that everything ran in the same direction. So if we do this trick here, high D equals high species diversity, low D, low species diversity. And then we'll see also that as we do these calculations, we get an index value that ranges between 0 and 1. And one of the advantages of Simpson's index is it has some statistical thought behind it, that it's basically a probability value. So it's reported as a decimal, but it does have a probability value associated with it, so it has some deeper implications. It's not as commonly used as the Shannon index, but Simpson's index to me makes a little bit more sense. Okay? All right. Let's take a look at how we would calculate this. Actually, let me write the equation up here first. So lambda is calculated out here as the sum of each of the individual abundance values multiplied by the abundance value minus 1, and all of this is multiplied by the total number of individuals times the total of individuals minus 1. And again, Ni is basically abundance for species 1, abundance for species 2, all the way up to the maximum number of species that I have in the population. Here, that's the total number of individuals in the population. Okay? All right, so that means that for this first one, this would be equal to 10 times 9 plus 10 times 9 divided by 20 times 19. Okay? That would be 180 over 400, 380. Okay? Which is the same as 90 plus 90 is 180 divided by 400 minus 20 is 380. So why isn't that coming out properly? I think I made the mistake on this one. So 180 over 380, I think I have a spreadsheet open here, equals 180 divided by 380 is roughly 0.47. I would report the D value here as equal to 1 minus 0.47 equals 0.53. Looks like in the table they're reporting the other way to refer to D. I'm going to use this index, but Simpson's index can also be represented like this. 1 over lambda equals D. So the reciprocal of 0.53 equals 1 divided by that value here is roughly 2, which is what we have in our figure. So it looks like the figure reports it as the reciprocal of lambda, whereas I'm doing it this way. One of the advantages of doing it this way, the way I've done it, is that the range is between 0 and 1, and it keeps you within this probability world. Probability values are decimals, whereas by doing this reciprocal of lambda, you get away from this kind of intuitive feel for probabilities. Okay? Notice that these values, however you do them, work out the same way. An increase in richness without changing evenness increases species diversity as measured by the Simpson index. Keeping evenness the same, keeping richness the same but dropping evenness reduces the diversity index. Okay? All right, so just two different ways to estimate species diversity. Okay? All right, now, it should be somewhat intuitive that if we can find numbers that, or indexes that describe a community, they're descriptors of that community, properties, attributes of the community, that what we're probably talking about is a closed community. Because if I had a pretty sharp ecotone between these two communities, I could come up with a metric that described this closed community, its richness, its diversity, relative abundances of all of the species. On the other hand, if we're in an open community, I could, I suppose, come up with something to describe the entire thing, but the whole point with an open community is it doesn't matter right how far you go, there's never any abrupt ecotone. So it doesn't make as much sense to think about these communities in the same way I would think about a closed community. Because I could measure those attributes here, but they're not the same as the ones here, or even here, or here. Does that make sense? The community of itself, to somebody that works in open communities, the community is not circumscribed spatially. There's no way to tell where it begins and where it ends, and therefore, if you can't do that, then you can't really easily come up with numbers to describe where these communities begin and end. So we don't tend to talk a lot about richness and diversity unless we circumscribe the community artificially, right? Here's this Presque Isle Bay. Well, the community of fish may include all of the fish out in the lake, but we're just going to say Presque Isle Bay because it's a comfortable place to right, insert boundaries for that community. Okay, so we could use those measures, but we have to artificially come up with a place where it begins and ends, and then it becomes rather arbitrary. Now, there is another approach that you might use, and that's to basically say, well, I don't really have a described community. What I have are basically associations of species. And then my community is not defined by the species that are there, but defined by positive or negative associations between species. This species tends to associate with this other species. Right? Species 1 tends to associate with species 2 positively, whereas species 1 doesn't tend to co-occur with species 2. That would be a negative association. And then I can use this trick to kind of work out what my community looks like on smaller spatial scales. So I want to run through an example with you. Let's start out from the mathematical approach, kind of a logical approach, and build our way up. So let's say that I had a particular area that I'm looking in, right? I've artificially determined what this area is, and I'm going to go out and lay out a bunch of quadrats. These quadrats are randomly placed within my community, and in each of the quadrats, I'm going to look for the presence or absence of species, right? I'm going to write down quadrat 1, species 1, species 2, species 3, etc. and I can go ahead and enter that information for each of my quadrats. Right, and so on. Let's say that there's only one species in this community. That means that each quadrat either contains the species or it doesn't. I don't really care about how many individuals are there. What I care about is whether that species is present or absent. Now, I could plot this up as the absence of species 1 or the presence of species 1, and I could put each of my quadrats. Let's say I did 10 quadrats, and let's say that 6 of them were zeros and 4 of the quadrats had the species present. That means in my big area here, and my quadrats that were laid out, I have two kinds of quadrats. Quadrats that have the species in it, and quadrats that don't, and those quadrats are bare ground. So these quadrats have the species present, and these have bare ground. Which means in thinking about this community, I would say to myself, well, gee, this group of quadrats are more similar to each other than this other group of quadrats. And therefore, what I have in this community is not a uniform, homogeneous species 1, but kind of spatial associations of the species and places where they don't occur. Okay? Now, let's say that I had 2 species in my community, species 1 and species 2. I'm going to do the same thing. Species 1, absence or presence. Species 2, absence or presence. Now, in my field, 3, 4, 5, 6, 7, 8, 9, 10, I have 4 kinds of quadrats. Quadrats that lack both species, those data points would be here. Quadrats that have species 1 but not species 2, that data point would go there. Quadrats that have species 2 but not 1, that data point would go there. And quadrats that have both species 1 and species 2 would go up there. So there are only 4 locations the data points can land. Let's say that the data points all land here or here. Let's say that 6 of the quadrats have species 2 but not 1, and 4 quadrats have species 1 but not 2. Is that okay? That means that out here I have 2 types of quadrats, one with species 1 and one with species 2, or another way to say this is species 1 and species 2 are negatively associated with each other. They don't tend to occur in quadrats together, for whatever reason. Competition, species 1 carries an insect around with it that negatively affects species 2, right? All kinds of reasons we could come up with. Okay? All right, now, in the mathematical world, I could distill all of this information down into a line, a one-dimensional measure, and that's this line. This line is a one-dimensional representation of this two-dimensional image. This line functioned a lot like this line, where I had presence or absence of species 1, and all of the quadrats were at one end or the other. Here, I have a line with all the quadrats at one end or the other, but the axis for this line, unlike this one, is different. This axis was species 1. This axis is a combination of species 1 and species 2. And it's a mathematical combination that's arrived at as a linear combination of the 2 variables. Okay? But this line, or axis, separates out the 2 quadrats best in this two-dimensional space. Now I could do the same thing with 3 species. Okay, 3 species now. Species 1, presence, absence. Species 2, absence and presence. There's species 3, presence, absence. Now, I go out and look at those quadrats. There are 8 places in this 3-dimensional space that these quadrats can exist. Quadrats could lack all 3 species. That would be a data point here. They could have species 1 but not 2 or 3. They could have 3 but not 1 or 2. That would be here. They could have 2 but not 1 or 3. Or I could have both 1 and 2, or both 3 and 2, or 1 and 3. Right? I'd have 8 places these points could exist. I could employ a trick just like I did before, and now all of these data points, instead of being in 2-dimensional space, are in 3-dimensional space. Think the room. Then what I could do is drive a line through that cloud of data, and that line is trying to separate out the quadrats in 3-dimensional space the best way possible. The only difference is now that I'm in 3-dimensional space, right, this line is somewhere like this, is now when I look at this line, it's a combination of all 3 species, a linear combination, and I'd have some data points perhaps at the 2 extremes, but I might also have some data points that exist in between, because when I force that line through 3-dimensional space, some data points are at this end, but some of them are not at either end. Okay? Sometimes people describe this as you take the line and run it through the 3-dimensional data cloud, and then you take a flashlight and you shine that flashlight through the data and the line, and that line and the data points get projected onto a 2-dimensional surface, which is the wall, but that line that's on the wall is a combination of all 3 variables.